So the question now, what is a register? All right. Now, if you've taken a CS class that gets into architecture, the architecture of a computer, of a processor and all that, computer architecture class, you'll know that you use registers in your assembly programming. So let's think about this a little bit, all right? And draw my box that I consider the black chip on your red board, that chip that's right in the middle. So I've really blown this up, okay? And we know that there's all those gazillion pins, 300 and some pins that come out to the world from this chip. And so far, all we've used those pins for was setting a pin high or setting a pin low so that it drives an LED, right? That's what we did with an IO pin, output pin. And then an input pin, we were able to see if that pin was high or low. In our case was whether a button was pressed or not. When it was pressed, that grounded the signal. Remember the push button grounded that signal, and so it was a 0. When we let off of the button, there was a resistor, a pull-up resistor inside the CPU that pulled that high, and so then we saw that as a 1 or 3.3 volts. Okay, well, besides the GPIO, there is a bunch of other things inside this CPU. I guess the major thing inside the CPU is its processing unit. And that's called an arithmetic logic unit. Okay. And that unit is what adds two numbers together. It also checks if one number is greater than another number, right? Some conditions. If a number is equal to 0, if a number is positive, if a number is negative, some different checks like that. This is where that processing happens. So this is the core of your processor where everything happens. So, and then there are what are called registers down in the ALU, a list of them that you can use when you write your code in assembly. Well, thank goodness, we're not going to write any assembly language in this class, okay? We're going to be doing it all in C. And the C compiler is in our world, when we're just programming in C, the C compiler is what knows about these ALU registers. And it knows, so you can actually do this if you're interested. There's a view mode in Code Composer. When you have your source code up, and especially if you're debugging your code, there's a way to view, well, even if you're not debugging, there's a way to view the assembly code that is generated by the C compiler. And you'll see in that, assembly code, these different register names, A1, I don't even know what the name of some of these are, but usually A1, A2, A3, or S1, S2, S3, for some names of these registers. And what happens is when, for example, when the ALU wants to add two numbers together. So we've got the ALU and we also have memory. Okay. And I drew these kind of small. Each of these registers are 32 bits. So it's just, you can kind of think of an array of 32 bits, places where the ALU can put things. Okay. And then we have memory. Now our memory is a little different than what you think of when you have your laptop, right? You go buy a laptop and, it has a Intel i7 processor in there. And then you have maybe 16 gigs of RAM, right? Well, that 16 gigs of RAM, I'm sure you know that is an external RAM. That's a little SIM, right? That's a little socketed SIM card that you put in your laptop. And if you want, you could upgrade that, right? You could add more memory and all this kind of stuff, possibly. Well, today, these laptops today are coming with soldered RAM these days, aren't they? Soldered to the board. But anyway, there's a lot of laptops still that you can upgrade your memory. For us, and that's why you're going to find with this processor, it's not really well versed in logging data just by itself with this, just the chip, because there's a limit to how much memory there is. The memory, if I'm not mistaken, we have somewhere around, I think it's 200K bytes of RAM. So I guess that's a capital B. K bytes of RAM. All right. Now, that's actually quite a lot for a microcontroller. If you go looked at your Arduino or something like that, it's got a lot less than that, your Arduino port. But still, there's no way close to 600 gigs or 16 gigs of RAM, right? Now, when we get to the Raspberry Pi, which we will a little bit next week in Lab 2, the Raspberry Pi has it has 8 gigs of RAM. So in that world, we have a lot more RAM to work with, okay? But on our little processor, we don't have as much. Now, this is plenty for writing any of the code we want. It's just not enough for like data logging, making long arrays, saving loads of array data and all that kind of stuff. That would be something this processor can't do. But what happens when we want to add two numbers? What happens is the assembly instructions, let's say our variable, call it Dan I or something, my index. That variable, I want to add 5 to it or some number, num, and that's another variable sitting in RAM. Well, the assembly code that's generated from your C file knows to grab this 32-bit value and store it in one of these registers. Okay. Also go and grab this num value, store it in a different register down here. Okay. Then do the add operation that the ALU uses. And then that addition goes into usually what's called an accumulator. Right. And so the result, whatever, is sitting here after that add is done. And then the solution, whatever that is, my value the addition value. So what I'm doing, right, is value equals Dan I plus num is what I'm trying to talk about real quick here. So then what happens is the solution to those two things added together gets put in the accumulator. The accumulator's value then gets shoved into value. And that's all done in assembly. And it's quite not a lot, but it's maybe, 5, 6, 7 lines of assembly code where we get to do it in one nice C instruction, don't we? Okay. So pretty neat there. Anyway, so that's this idea of worker registers when it comes to your processors. And even if you go to Code Composer here, and let's see, if you go to the debug menu, let's see, I'm not going to show this. I won't be able to show this, I don't think. But if I go to the debug, it's not there. Well, yeah, sorry, but it's under here. You can go to View Registers right here. And once you do that, I'm not connected to a red board right now. Sorry, my computer, so I can't show this completely. But if you go to View Registers and then you go to the core registers, that's what this is talking about. These are the core registers of the processor, okay? The ones that we use to do our operations. Now, there's a bunch of other registers that we're going to get involved with. We're not going to get involved with these. We're not going to deal with assembly code. What we're going to get involved in are what are called peripheral registers. And so you guys have already played with peripheral registers. That is these guys, right? This register, let's make a new project, new, import CCS projects, browse. And because last night I installed a lab starter, imported a lab starter, I should say. So I'm already to my folder, right? Deep into the examples. So I can go find homework starter. All right. And just to get in the habit, you always rename this. It'll save you a lot of headaches if you get in that habit. And I'm going to call this homework lecture. Any name is fine besides homework starter. All right. And then you could rename this C file to whatever. Rename and call this lecture. Good. So you guys, as I said, we'll go to the main file. You guys already played with registers, and that is these GPIO registers, right? And it's kind of neat. As you get into them, this is going to become helpful. If you type in GPIO data regs for registers, that's what reg stands for, and hit dot, it auto completes for you, or well, it comes up with all the different options you have. And we guys went through a lot of these. Remember, we got GPC set, GPC DAT, GPC clear. Remember all those? Well, these are all registers that control the IOs. So that's a little section in our project. So toggle, and then we can say dot bit, dot, and then our different GPIO. And I'm going to come, hopefully I get to, before we're done here, I may not. If not, I'll talk Monday about these things called bit fields, but let's see how far we get. Okay, and that's what you're using here, but that's a register. Okay, let's go back here. So a little section of the board, if you want to think of it this way, is the GPIO registers or GPIO peripheral. Okay, so we talk about the GPIO peripheral and then the registers that control that peripheral. In the same way, we're going to talk about the enhanced PWM, pulse width modulation. PWM is a way to generate a square wave that you can change its duty cycle. So you could make a waveform that's, say, 25% on and 75% off. Does that kind of make sense? And so we'll talk more about that. And we can use this varying duty cycle to drive a motor. Okay. So there are peripheral registers inside this PWM that we use, that are used to set this up. Because we may want to change the duty cycle to 35% duty cycle. Well, there's a register. It happens to be called Compare A, CMPA. And by writing the correct value to CMPA, you'll get a change in duty cycle. And this almost looks like a variable that you use, and it kind of is in C code, but the difference is all the variables you create are sitting in RAM. When you say int 16tj equals 0, you are creating a spot in RAM for the j variable. These guys, Compare A and all that, they're already there. They are created really by the silicon. When TI made this chip, this Compare A register is sitting there at some spot in the processor. It's actually in what's called the address space. The address space of a 32-bit processor, it goes from an address 0 to address 4 billion, blah, 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 blah. So because we don't have 4 gigs of RAM inside here, we only have this 200 kilobytes. So only a part of the address space is RAM. All the other address space is for other things, for flash, for these registers and all this. And we'll get into that more. Where are these located in memory space? Not actual memory, but the space where memory could be, or is it kind of to say it that way. But anyway, so there's a difference between you creating a variable, float, value equals 0.0, compared to you using these registers that are already there. So the trick is, of course, always finding the right register, finding the name of the register, okay? Well, that's where there are, TI is very helpful with Code Composer in that, again, if you know the starting register name, for example, PWM is EPWM like we have 1, 2, 3, 4. I think there's 12 PWMs. So EPWM 1 regs happens to be the name, dot. And then here are all those. Oh, there's compare A. That's nice. All right. That's the one I was just talking about. But here's all these registers for the compare. All right. And there's a bunch of reserves also, but we'll get into that reserves. Now, are you going to need to know what every one of these do? I don't know what every one of these do. Okay. How do we find out about that? Well, that's where this tech ref comes in. How do we know what to set these PWM registers to? Well, yes, there's the tech ref, but what do I always go to first? Example code. Okay. So I always dig through all of TI's example code before I understand how to use the PWM. Yes, you do get a lot out of the tech ref, the technical reference, but it's definitely for you guys doing it first time, it is definitely confusing. Okay. So you got to kind of jump between the reference and your example code that you find. Now, of course, you guys got another avenue, and that's talking to me, talking to the TAs, reading through my labs, because as you in the labs and the homeworks, I give you this name and all that. So, you're down a little bit easier road than a person just, going to the website, say, hey, I would like to use this processor, and just looking at the tech ref and TI's example code. So you guys are in a little bit better boat. But let's see this. So EPWM1 regs has all these registers. And just to complete for just a second, back to the OneNote. Now, there's EPWM, there's all sorts of other things. We're going to be talking about the ADC units, analog inputs. There's a DAC unit for analog out. There's our serial ports. We're going to be talking about an SPI. And remember, we had an SCI we talked about Monday in lecture. Every one of these peripherals have their own set of registers, okay? And where do we find those? If we go, and I have it already pulled up, but if you go to the website, now just do it this way. What I did is, I'm going to show you this one just in a second, the full reference. This is this thing, it's got 2,800 pages or something like that. I went into that reference and pulled out the important pages for all the peripherals we're going to be looking at. Okay, so I have the ADC, I call it condensed ref. So I took out some of the things that are a little maybe confusing or more important that just we are not going to use. I pulled out of the reference. Okay, so obviously these are going to be the ones you're probably going to want to look at more. But just so you see it, and we may find a time when you got to go pull up this guy. Oh shucks, yeah. I'm going to do it a little. I'm going to show you here. When you pull this up in Chrome, it doesn't show all the chapters. So when you pull it up in, see if I can, yeah. If you pull it up in Acrobat itself, did I not put it there? Oh, shucks. Okay, I can download it. Let's do that quick. Come on, Dan. If I download this and then open it with PDF with Adobe, show in folder. Okay, it gives you all these chapters, which is really nice. Okay, so you'll want to, maybe there's a way to do that in Chrome, but if you pull it up in Adobe, you've got all these chapters. And see, then we get into the DAC chapter, the ADC chapter. This is the chapter I pulled out into the condensed ref and got rid of the things that aren't necessary for you to understand, at least for this semester in the class. And so let's find the PWM chapter that we were just doing right here. Enhanced pulse width modulator. It's so funny they call this enhanced. It's been enhanced for about, at least 15 years. It's pretty funny. There used to be a series of, we do the C28 or the F28 chips. There used to be a series of F24 chips. And so all the peripherals of the F24 got enhanced with the F28s. So that's where that E comes in, unfortunately. But again, we got this chapter here. Look always at the bottom of the chapter. of all these different peripherals are the EPWM registers. Okay. The description of those registers are mainly up in the explanations up here of doing these. So a lot of these, we're not going to do deadband. We are going to do action qualifier though. Let's see, what aren't we going to, we're not going to be doing any of this X bar and all this. We are going to do event triggers. So, you know, so some of this we need, some of this we don't. We're not going to do high resolution pulse width modulation. Now, all these registers, click on it. If we go down to this page, it lists off, see, there are 12 PWMs. And each of these PWMs have all these registers. And here it lists them all off. Again, we don't have to look at all these, but it's just a long list of things we got to understand. Now, well, and some of these we have to understand. And then if you go and say the go button here, say on timer-based control is what TB control means. If we go down here, we don't even know how a PWM works yet. I'm just trying to get you to understand this idea of a register. We come down here and see this is this 16-bit register called TB control. And notice here, for example, bits 14 and 15. TI has named that free soft. Okay. And what's neat is TI, whatever they name it in these bit fields that I'm showing you in the C code, they're going to give it the same name as this chart. And so that makes this really easy. So if you want the option here for free soft, since it's 2 bits, you can set it to 0, 1, 2, or 3, because it's only 4 bits. So it breaks this down. Instead of you having to set the entire 16 bits, all you have to think about is what free soft needs to be. Or you can come down here and see what you want clock divide to be. Clock divide right here is, where's that? Clock divide right here is 3 bits. Bit 10, bit 11, bit 12. And by setting those 3 bits to these possible 8 different states, 0, 1, 2, 3, 4, 5, 6, 7, 8, 7, 0 through 7, 8 values, you can change the divide. Well, you don't know what that means yet, but at least right now you know that there's a way to change this thing called clock divide. Okay. And real quick, let me show you, we're almost out of time here, but let's go back to Code Composer here. And look at this. So if I go EPWM1 regs dot, all right, I can go find TB control, that register that we were just looking at, right? So we're looking at TB control right here, right? TBCTL. And TI with these bit fields does a really good job of keeping the same names. So we can do this, hit the dot, and then TB, and there it is, TB control. We can hit enter and then hit dot again. Now, if you want to set all 16 bits at the same time, you can do all. But if you want to do it with those bit fields, you can say dot bit. And now notice, TI gives you all those options. And the great thing is it makes them the same names. So it makes it easy on you. You can now, okay, there's clock divide, there's phase direction, whatever that is. And you can come down here. And a lot of times this explanation right here is plenty for you to know if you want it to be 0, 1, 2, or, you know, if it's just 1 bit, it's just 0 or 1. Do you want to count down after the synchronization event, or do you want to count up? Well, of course, you got to understand what that means. But once you read that, you're like, oh, that's right, I read that. And we want to count down. So you'd set it equal to 0. Okay. And so back here, you know, so we got dot bit. And then, okay, let's do clock divide. Clock divide, right? We can set that to any number between 0 and 7, right? Because it's 3 bits. Okay. So we could set it to 4 or something like that. And if we do that right there, then we've just set up the counter, the clock divide. We set it to 4, which is this right here. We are dividing something by 16. Well, it's a clock. And what that is, the clock is, the divide is the clock coming into the peripheral. A lot of times that's 200 megahertz. For this guy, it's actually 50 megahertz, and we'll get into that next.